There we go. There's that. There's that other thing. And this thing. And we're ready to go. Welcome, folks. Finally get to learn about power series. Power series are like infinite polynomials. In a way, it's a function. Okay, function of x. Basically, we're going to take the concept of an infinite series that we've been studying, and we're going to throw a variable in there, right? Just say, hey, let's make an infinite series, but put an x in it. And then you're adding up a bunch of terms that have x's in them, powers of x in particular. And then we'll study whether that converges. And this convergence now is going to depend on the value of x. So anyway, what does it look like? The idea is we're going to adjust things a little bit. Instead of having n start at 1, we're going to have n start at 0 and go all the way to infinity. And then we'll have some coefficient, which we'll call Cn, multiplied by a power function, x to the power n. So what this is going to look like is a C0, which would be the very first of the coefficients, the very first number in this sequence called C, times x to the power 0. That's the first term. Now x to the power 0, remember, is 1. And we're going to assume here that x to the power 0 equals 1 always, regardless of x. So like even when x equals 0. Okay, so this is a little bit of like, we have to just like sort of arbitrarily define this, because normally 0 to the power 0 is considered undefined. And, or if not, it's sort of, 0 to the power 0, if you have a limit in the form 0 to the power 0, it's called indeterminate. So what exactly does 0 to the power 0 equal? It's not totally clear, but in this context, we are just going to define it to be equal to 1. So that means that I can just scribble out this x to the power 0 and say that basically isn't there. We have a first term in our series, which is a constant term, just like how a polynomial has a constant term. And then we have C1 x to the power 1. That's going to have x in it, right? Plus C2 x squared. That'll have an x. C3 x cubed, so on, okay? And this will go on not just for some finite number of terms like a polynomial does, okay? If I were to just stop, right? If I were to just stop with this sum and just say it goes up to x to the power 4 and then it stops, that would be a polynomial. That would be a 4th degree polynomial. But what if it goes on forever and never stops? Then it's a power series. So that's why I say that power series are basically just infinite polynomials. Okay? Okay. So, for example, if you have a formula of some kind, like let's take the formula Cn equals 1 over n plus 1. It's sort of like 1 over n. It's almost 1 over n, except that because for this purpose, we're starting n at 0 so that we can have a constant term, okay? For this purpose, starting n at 0, we want to do 1 over n plus 1. So that way it kind of starts with 1 and then goes a half and then a third and then a fourth. And it's kind of offset from the n value by just one value. So, so this is basically the harmonic series, okay? Or except that now we're talking about plugging in, or sort of taking that harmonic series and multiplying it by these powers of x. So what you would get from this, written in this format, it would be like 1 over n plus 1 and then times x to the n. This is going to be 1, because it's 1 over 0 plus 1 times x to the power 0. So the first term is 1, and then we have a half x. Then we have a third x squared. a fourth x cubed, 1/5 x to the power 4, etc. forever. So that is the example, the first example we'll look at. So the question we want to ask is, well, what is this? If you plug in a value for x, what sort of series do you get? Okay, let's call this, so this is our f of x function, okay? Well, what if we do f of 0? Let's start there. If we do f of 0, then what you get is 1 plus a half times 0 plus a third times 0 squared plus ... Obviously, anytime you multiply by 0 or 0 squared or 0 cubed or anything, those are all going to be just 0, right? So those are all going to go away. And all we have is just 1. So what this means is that f of x, the series, converges to 1 when x equals 0. Basically, it's like when x equals 0, it's a super boring function that it's just 1. Like it's a constant function, in fact. And if it's a series, it's 1 plus 0 plus 0 plus 0 plus 0 forever. The rest is all zeros. So it's a really boring series. Let's look at something a little more interesting. Let's look at f of 1. Okay, if I plug in 1, then I'm going to have 1 plus a half times 1 plus a third times 1 squared plus a fourth times 1 cubed. This is all of these powers of 1 are all equal to 1, equal to 1, equal to 1, equal to 1. They're all equal to 1, right? So then if I keep going with this, plus ... forever, essentially what I get here is just 1 plus a half, plus a third, plus a fourth, plus etc. And now that's just the harmonic series, which is indeed divergent. Okay, so we've seen an example of, we would basically say f of 1 is undefined. F of 0 equals 1, but f of 1 is undefined. Okay, so this function we're creating, which is this infinite polynomial, only gives you a defined output if the series that corresponds to that x value converges. So we've seen one of each. Let's look at another example. What if I take where f of 1/2? F of 1/2. Now we have 1 plus a half times a half plus a third times 1/2 squared plus a fourth times 1/2 cubed, etc. Okay. Well, does that converge or diverge? If I were to write it out as an infinite series, it would look like that. It's very similar to it's sort of like almost like a power series and a geometric series multiplied together, because it's sort of like, this is basically like a power series, like a p series, not a power series, a p series, which is 1 over n. It's 1 over n plus 1. It's really close to the harmonic series. This is a geometric series. Harmonic series diverges. The geometric series converges. What happens when you multiply them together? And it's not like multiplying the entire series together. That's not what this is. It's just multiplying them term by term, right? Corresponding terms multiplied together. What happens? What is that? Well, Here's one way to look at it. If you kind of isolate those coefficients here, those fraction coefficients that are from the harmonic series, you look at those. What if I were to remove those? So let's write it without those. Okay, if I don't have those anymore, did I make it bigger or make it smaller? So I removed some coefficients that were fractions less than 1, a half, a third, a fourth. So the result after removing those should be bigger, right? Got to be larger, right? So the inequality should be that. Agreed? Correct. So now what I've got here is just basically 1/2 to the n. It's a geometric series. With r equals 1/2. So convergent or divergent, this series. Geometric with r equals 1/2, convergent, right? So what I've actually done here is taken the series we're looking at when f of 1/2, right, which is this series that has these coefficients in it. If I remove the coefficients, I make it bigger, and I get a convergent series. What does that tell us overall? And what test am I talking about here? Yeah, this is comparison, folks. That's right. This is comparison. So what we're seeing here is we made it bigger, and so by comparison to this larger series which converges, this series must also converge. It does satisfy the requirements of the comparison test because these are all positive terms. They are decreasing in value, so we're all good there. So I can say that f of 1/2 converges by comparison test. Okay. Yeah. So there again. So now we're kind of we're saying f of 1/2 equals something, but we're not sure exactly what it is, right? So figuring out actually what that converges to would be a useful thing to know, because it would tell us what the output of this function equals. Okay, but we are not actually there yet. We're not actually to the point of being able to do that. We'll get there. We'll get there. But yeah, so examining this weird infinite polynomial function, we can see sometimes you plug in an input and you get an output, right? Like in these cases, sometimes you have a defined output. We're not always sure what it is, but it should converge to something. Whereas other times it's undefined, right? You can also try putting in something like -1 to this function, right? If you do f of -1, what you get is you get is 1 plus 1/2 times -1 plus 1/3 times -1 squared plus 1/4 times -1 cubed plus ... Do you recognize that one? 1 minus 1/2 square -1, you get back to +1 plus 1/3, and then cube it and you get back to negative. We have it alternating. Yeah. So this is the alternating harmonic. it is conditionally convergent, but in the order that it's written here, we can say that it converges. And f of -1 equals the natural log of 2. Okay. So these are strange functions. Okay, these functions called power series, they have like some values, some input values where they converge and other input values where they diverge. Okay. We're going to explore that concept. All right, so turns out there is a theorem on this subject of convergence. Okay. It says that a power series, well, let me phrase this right grammatically. For a power series, which is what's called centered at a given value, a number A, which looks like this. So right here, this x minus a is something. This is new here. This is I didn't talk about this earlier. This idea that a power series can be sort of centered at a different value is kind of important. It's the example I gave earlier, and when I first wrote down what a power series looks like, I actually gave you a power series centered at 0, right? Because we didn't have this minus a here. Basically, it was x minus 0, and we were just looking at powers of x. But if you put a minus a inside there, then essentially what that does is it shifts the function so that it's where 0 used to be is now at x equals a. You know how if you subtract a number from directly from x, it shifts it to the right by that amount, or if you subtract a negative number, it shifts to the left. That is like a horizontal shift that you learned about back in pre-calculus. That's the idea here. Okay, same sort of thing. This is called centered at the number a. Okay, so for a power series like this, there are 3 possibilities. One, the function, which I'm just going to call f here, f of x will converge at x equals a, but diverge for all other values. All other x values. Okay. The second is it could converge everywhere. Just all x values. And the third, the only other possible situation besides converging at one place or converging at all places is this. Converge for all x within a distance called r, capital R, for radius from a. In other words, converge if x minus a is less than r. And diverge if x minus a is greater than r. Okay. So that means that there would be this symmetrical interval around the number a in which it diverges, or sorry, in which it converges, but it diverges outside of that. Note, when the distance between x and a actually equals r, it could converge or diverge. Just sort of depends. These are the end points of the interval, and that you have to check them individually. You can't say with confidence. You have to just check them. So to diagram these out, here's three. We're going to draw number lines. And we'll diagram out the three possible situations. Okay, one thing's for sure. It always converges at a. When you plug in a to a power series centered at a, let's see what happens. F of a is always going to be C0 plus C1 a minus a minus a plus C2 a minus a squared plus dot, 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 dot. And as you can see, whenever I do a minus a, it always equals 0. So the result is C0. Like plugging in the number 0 or plugging in the number a makes it so that it's like your square, the powers are all 0, powers of 0, right? This was similar to plugging in 0 for the power series that was centered at 0, the first example on the first page. Like everything goes to 0 except for the constant term. Clearly going to converge. So that basically in number 1, in case number 1, that's the only place where it converges, and it diverges for every other possible value. So in case number 1, we will say it's diverging over here. Let's make that nice and orange. Diverging over there, diverging over here. So diverge, diverge, and convergence happens only right there. In case 2, it's like, you know, it doesn't matter what x value you plug in, it just converges all the time. It converges everywhere. That's case 2. And then case 3 is, okay, it converges within a radius around the center. Those are wrong type of braces. There we go. Let's draw my braces a little better. There we go. So that is the distance r on the left and the right side. Okay, so over here we have a minus r, and this is a plus r. And this situation is where it converges in here. And then it diverges over here, and it diverges over here. And then what actually happens at the endpoints is questionable. You have to check it, like I said earlier. It could converge or it could diverge. Okay, so that's the diagram that explains, like, it turns out, and I'm not proving the theorem, but there's no other situation. It can't, like, for example, converge at a and every number to the right, but not every number to the left. Like, that's impossible. It can't be an asymmetrical distribution around a. And also, what's interesting about this is you can't have a situation where, like, it converges on an interval here. You can't have it converge for a little bit and then diverge and then converge and then diverge and then converge and then diverge. Like, that never happens. You don't have these separate, you never have, like, separate intervals of convergence. If it converges for some x values, it only ever does it on an interval around a that's symmetrical. So, okay, so that's something to bear in mind moving forward. Now, how do you actually figure out what that interval of convergence is? Like, how do we know basically, like, what's the domain of a power series? What's the domain of a power series function? Okay. So if f of x is defined by a power series, what x values are the valid inputs? The answer to this is x values within that interval of convergence. Okay, so finding the interval of convergence is like finding the domain of the function. Okay, that's just a way, to like frame this question and think about it. So it's just like, you know, obviously like the technique is going to be totally different, but the type of question we're asking is just like finding the domain of a function like you did back in pre-calc, where you say like, oh, let's make sure we're not dividing by 0, or we're not putting negatives under square roots, like that kind of thing. Except this time it's more about like, oh, let's make sure that the x value is gonna give us our convergent series as opposed to a divergent series. So that's what we'll be doing. Now, the technique for determining this comes down to the ratio test. Okay, the ratio test is probably the most useful tool for determining this sort of interval, this thing called interval of convergence. Okay, let's go back to our example. The one we were working with on the previous page, which we'll label f of x, and it's this 1 over n plus 1 x to the n. So remember, this is centered at 0. Okay, so this is like the 1 plus a half x plus a third x squared plus dot dot dot. Remember that one? So if we apply our ratio test, we're going to say rho is equal to the limit as n goes to infinity of the ratio of the n plus first term divided by the nth term. Like that. That was our ratio test. So if we do the n plus first term, it'd be like taking this and replacing n with n plus 1. So we actually have 1 over n plus 1 more. Okay, so this becomes this when you replace n with n plus 1, right? Now we have 1 over n plus 2. And then this is x to the power n plus 1, right? Let's put that in the numerator. That's, you know, since it's multiplied, we can put it up here, x to the n plus 1. And then when we divide by the an, it's equivalent to multiplying by the reciprocal. So we're going to have n plus 1 up here and x to the n down here. Okay, so this is our, you know, an plus 1 divided by an. I want to make very clear that that plus 1 is in the subscript and not on the same line as the an, as the a. It's subscript plus 1. Yeah. Okay. So this is going to be a little bit of a hard limit to explore because it's got two variables in it. It's got x, which is a real value variable, and then it has this n, which is an integer variable, and we're taking the limit as n goes to infinity. But the fact that this x is here means we're not really going to be able to solve this limit definitively because it'll depend on what x equals, right? But that doesn't mean that it won't still be useful to us. So we can simplify this. You'll notice here in the ratio test that xn cancels with this, and we just have x in the numerator, like it's just x. Okay. Now, I'm going to separate out that x. So that x, I'm going to separate it from the rest of this stuff. Now, I have absolute values here. I'm not going to forget about the absolute values there. Okay, so we have the absolute value of x. I'm separating that on the side, and then I have the n plus 1 over n plus 2 right here left over. Okay. This x is as far as the limit is concerned, because this limit is focused on the variable n, that absolute value of x is treated in the same way that you would treat a constant. So as far as the limit's concerned, we can pull that x out of the limit like we would do with a constant. So that we can say now, this is the absolute value of x times the limit of the absolute value of n plus 1 over n plus 2. And that limit we know, right? We can compute that limit. This is just equals 1 over 1 because it's a limit of a rational function, right? You take the ratio of those leading coefficients. So this all just equals the absolute value of x. So, hey, that's awesome. That's nice and simple. But what do we do with this? Well, remember that the ratio test has three results, right? It says if rho is less than 1, then the series converges, right? If rho is greater than 1, then the series diverges. And if rho equals 1, then who knows, right? It's inconclusive. So because we got rho as a function of x, we can now turn these three situations into statements about x. We can say, hey, our rho, right? We just found out that rho equals the absolute value of x, and there's nothing else going on, right? And that's just, I mean, if this limit had given us some other number, we might have had like a times 5 over here or whatever, you know, or like a times 2/3 or whatever that whatever that limit ended up equaling. Okay, but we just got it equals 1, so it's just this. So that means we replace our rho in these inequality statements with whatever the function of x is. So we're going to say if absolute value of x is less than 1, then our series, which we now can refer to by the name f of x, since it's a function of x, right? Our power series f of x converges. If it's greater than, if that absolute value is greater than 1, power series f of x diverges. And if it equals exactly 1, then inconclusive, right? So what do we have here? We have it's convergent at 0. It's convergent between, as long as x lies between -1 and 1, right? So we have this interval where f of x converges. That's what the ratio test says, right? And that's this, right? We have this interval. We have anything outside of that interval when the absolute value of x is greater than 1. That's where it diverges over there and over there. And then when it equals 1, okay, when it equals 1, that would be our -1 case and our +1 case. But we happen to have already examined those two cases. We already found that f of -1 was the alternating harmonic series, natural log of 2. And f of +1 was the regular harmonic series, which is undefined, right? It's divergent. So we can say it converges here and it does not converge here. So the domain of this function, essentially, the interval of convergence, is -1 to 1, including -1, and this is interval notation I'm using now, but not including +1. And so that is the interval on which this function is valid. It has an output. Okay. I'm over here. I'm gonna pull up Desmos. We're gonna take a look. I think Desmos should be able to do this. Oh no, my poster fell down. That's what I get for opening my window. So let's do a sum from 0 to infinity and do 1 over n plus 1 times x to the power n. Does it like that? No, it doesn't like that. Oh darn. If I go to like 100 or like 1,000 or something. You can kind of see what's going on here. So you can kind of see here that this is what it looks like if you add up to 1,000. Okay, so this is just an approximation of that function with a partial sum. Okay, but adding up to 1,000 should get us pretty close, right? So what it basically looks like is it basically looks like this. This is basically what it looks like here. When we're equal to -1, it actually is going to converge to something, and what it should converge to is the natural log of 2. So let's y equals natural log of 2 is there. There we go. So yeah, that's the natural log of 2 right there. That is what this converges to. So it's getting closer and closer and closer to like hitting the natural log of 2. And what actually is happening here is because we're working with an approximation, it kind of like diverges at the last second. But what it will do if we were to take this all the way to infinity is actually converge. On the other side of things, though, over here, when we get to x equals 1, what's happening is instead we have this very clear vertical asymptote where it's clearly diverging to infinity. So this over here is the harmonic series. This is the alternating harmonic series. And we have this sort of half open, half closed interval of convergence. Okay, for that power series. So there we go. I think that is the end of that example. That's pretty cool. I'm just going to, I guess for the record, I'll go ahead and stick this in the notes. You guys got any questions? I hope it makes some sense. This is like a totally new type of function, you guys. We've had algebraic functions. We've had like functions you define with integrals. Back in Calc 1, we had those. Back in Calc 1, we introduced a new type of function, which was like an accumulation function defined with an integral, remember? We'd never seen a function like that before. But now we have these power series functions where sort of like defining a function with an integral, except you're actually like literally adding up an infinite series to define your function. Yeah, so we can study them in all the same ways we study other types of functions. Okay, let me check my notes. What's next? We have 10 minutes. So we have, so yeah, we've done the ratio test on our first example to find the interval of convergence. Oh, by the way, in that example, the radius of convergence was 1 because it was like between -1 and +1 with 0 in the middle. So that's a radius of 1. Does that make sense? It's called a radius, even though it's not technically a circle. It's just an interval, but it's sort of like a circle if the circle was only in 1 dimension. Yeah. Yeah. So let's do another example. Oh, this is a quick example. So for example 2, we'll look at what if you define it as just x to the n. So basically we're saying like Cn equals 1. This is just 1 plus x squared plus ... forever. Well, what's that going to look like? It's still centered at 0. So we know that it's going to converge at 0. What if you pick a different number? What if you pick like f of 1 again? Then you'd have 1 plus 1 plus 1 squared plus 1 cubed plus 1 to the 4th plus ... What's that going to do? Converge or diverge? It's 1 plus 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 1, kind of forever. Yeah, I mean, forever. You keep on adding 1 forever, you're going to diverge. What if we have -1? 1 plus -1 plus -1 squared, which is back to 1 again, and then plus -1, and then -1 squared, which is back to, or sorry, the 4th, and then -1 for when you go to the 5th power. And it's going to start alternating 1 plus -1 plus 1 plus -1, back and forth like that. Do we know if that converges or diverges? This is the one where physicists and mathematicians disagree. Partial sums of this are really weird. The partial sums go 1, 0, 1, 0, 1, 0, 1, 0. Because every time you add 1, you get 1, and every time you subtract 1, you go back to 0 again. And so the partial sums just flip-flop back and forth. We say this diverges as well. That's oscillating. Oscillating type of divergence. This is infinity, but that's oscillating. What about between them? What if you did like f of a half? Then you'd have 1 plus a half squared plus a half cubed plus a half power 4. Oh, that converges. That converges. That converges to 2. We proved that on like the first day we studied, on the first day we looked at infinite series, we proved that converges to 2. That's just geometric, right? That's just a geometric series with r equals a half. In fact, actually, f of x is a geometric series with r equals x. So we should just be able to literally just grab the rules for geometric series, just what are the rules for geometric series, apply that to x, and bam, that's the convergence of this function. So actually we can just say, and this thing converges if the absolute value of x is less than 1, and diverges if the absolute value of x is greater than or equal to 1. That's it. So the interval of convergence, otherwise known as the domain of the function, is -1 to 1, this time not including either of those -1 or 1. We don't include either of them. So that's our domain. Let's look at one more. Example 3. Let's look at summing n equals 0 to infinity 1 over n factorial x to the power n. This is a good one. So now we've got like 1 over 0 factorial x to the 0 plus 1 over 1 factorial x to the 1 plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, 1 over 4 factorial x to the 4th. So this is 1 plus x plus a half x squared plus a 6th x cubed, because I think it's 3 factorial is 6, and 4 factorial is 6 times 4, 24. So 1 over 24 x to the 4th, and so on. Okay, so that's that power series. If we want to figure out what its interval of convergence is, we can apply that ratio test, like I said earlier. So if it's not obvious by some other method, ratio test is your best friend. So we do the limit, and it goes to infinity. We do the n plus 1 version, which is x to the n plus 1 over n plus 1 factorial. Okay. And then divided by the n version. So I'm going to multiply by the reciprocal of the n version, which is that. So now we have all of this nice canceling that happens. X to the n cancels with that, and we just have an x in the numerator. And then you may remember how this works. Have you guys done a few of these ratio tests now with factorials? May remember that n plus 1 factorial is like n plus 1 times n factorial. So the n factorial cancels and the n plus 1 is left over. So all we have here after simplifying is x over n plus 1. So absolute value. So the absolute value of x comes out. So we have rho equals the absolute value of x times the limit as n approaches infinity of 1 over n plus 1. There's n plus 1 in the denominator, but the numerator is just 1. So 1 over n plus 1, as n gets bigger and bigger and bigger and bigger, we're talking 1 over larger and larger and larger numbers. That's clearly going to 0, right? So that's going to 0. So this whole thing is just whatever x equals its absolute value times 0. Okay. Well, x is a real number, and every real number times 0 is 0. So that's 0. So what does the ratio test tell us when rho equals 0? I believe if we go back to our ratio test, if you look it up in the on your reference sheet that I gave you guys yesterday, which you will be allowed to use on quizzes in the final exam, the ratio test says when rho is less than 1, the series converges. Well, 0 is less than 1. So the series, so the function we're looking at, this power series, f of x, always converges. It doesn't matter what the value of x is for this particular example, because whatever x is, when you do the ratio test here and you do this limit, you get x times 0. And so rho always equals 0 for every x. So it always converges for every x. So in this case, our interval of convergence is equal to the interval from negative infinity to infinity, like that. It's the whole thing. This is one of those examples where it converges everywhere. So so now if we go back to Desmos, we can look at what this one looks like. So now I'm going to do factorial down here and let Desmos think about that. It can take Desmos a few seconds to figure out how to draw the graph, because we're asking Desmos servers to do a lot of work here. There we go. All right, that's what it looks like. That is a rough picture of x to the n over n factorial. Does that look familiar to you guys? That graph? That's right. It's y equals e to the x, which is not a horizontal line as it may appear right now. I think I'm honestly just overloading Desmos. There we go. There's e to the x. Yeah. So that e to the x, so that particular power series actually equals e to the x. And that, my friends, is our first example of a Taylor series. So actually, equals e to the x. These are the same function. And that is, I mean, that's pretty mind-blowing. I think this is the example I showed you guys at the beginning of this unit when I told you this is where we're going. This is how you can take a function and write it as an infinite polynomial. Okay. So we'll dig deeper into that in the coming weeks. Okay, everybody. Have a lovely day. See you tomorrow. Oh, what am I doing? I was already in the right place and I already had everything perfect and then I messed it up. I did mention a reference sheet being handed out yesterday. Yes. If you weren't in class yesterday, when you're in class tomorrow, I'll give you a copy of that. It's just got all the series convergence tests and also some common Taylor series.